Okay, so this is a joint paper with Melanie Schiele, who is at the University of Hanover, or was at the University of Hanover and now moved to Karlsruhe, and she will actually present this afternoon another paper, and it's about misspecification testing in Gauge-Midas models. The idea of these models is that you have a two-component model of volatility. One is a gauge specification, the other one is driven by macroeconomic explanatory variables. And what we want to do is we want to test whether these exogenous variables really drive volatility. Okay, why are we interested in this? Here's a quote from a paper by Engel where he says that prior to the financial crisis, standard risk management primarily focused on short-term risks, such as 1 day, 10-day ahead value at risk. And he claims that this creates a problem because what you miss is the fact that there is a risk that risk will change. And so he says what you should look at is value at risk over longer horizons because, for example, if you are in a, say, low volatility regime currently, then there is a high probability that volatility is going up subsequently, and you should somehow capture this risk. And partly we have seen this in Claudio's presentation at the first slide, where you have seen before the Great Recession, volatility of global activity was very low, but then it increased dramatically. Okay, so if you want to do this, then you have to think about how to forecast long-term volatility. And our idea is that we will use that stock market volatility, or the secular component of it, is related to the development of the macroeconomy. And actually it behaves counter-cyclical. So if the economy is booming, volatility is low, and if you're in a recession, financial volatility is high. And so we have a previous paper on this where we show that, for example, the term spread, housing starts, or survey expectations on future industrial production, all these variables tend to anticipate changes in the level of financial volatility. And this is what we want to exploit. So here's one graph which illustrates this fact. So the circles here all show quarterly realized volatility in the S&P 500. And you see that sometimes it's low, sometimes high. This is the 87 stock market crash. Unfortunately, you can't see the recession shadings here, but they are somewhere in the plot. And what you should see is financial market volatility is high during recession periods, and low in boom phases. And what you also see are this bold black line and the dashed line. And the dashed line is the estimate of the conditional volatility that you obtain from the Gauge-Midas model. And then the bold line is what we call the long-term component. And this long-term component in this example here is entirely driven by the term spread as the explanatory variable. And for example, what you see is before the last crisis, this long-term component really increased long before actual realized volatilities were increasing. And so this might help you to anticipate that volatility will increase in the future. And what we want to test in the end is whether the term spread predicts volatility. And basically this means that we want to test whether this bold black line here is flat or not. So the null hypothesis will be this is just a straight line, and the alternative, say the term spread, can explain how the secular component in volatility is changing over time. Okay, the model is a two-component specification. There are a couple of component models that have been previously suggested in the literature. Most of them were additive. This here is a multiplicative specification. So the short term is gauge, long term depends on exogenous variables. There is one paper which provides asymptotic theory for the QMLE estimator of the model, but only for the specific case that the explanatory variable that you use is realized volatility. But not for the general case. Okay, so the test is a Lagrange multiplier test, which means that we have to estimate the model only under the null. And under the null, when the long-term component is flat, you obtain a simple Gauge specification. And yeah, you can view this as an extension of the arch nested in Gauge test of Lundberg and Terres-Virta, and it's also related to Halunga and Orm, who suggest a misspecification test for Gauge models, and more recently Amado and Terres-Virta. Okay, so how does the model look like? So the epsilon t's will be our returns. We assume that the returns have mean 0. And then we have the set T innovation, which is IID, with mean 0, variance 1. And the conditional volatility is decomposed into the tau. This is the long-term component, and the H, which will be the short-term component. HT is just a simple Gauge 1, 1. And we fix the constant in the Gauge 1 such that the unconditional variance of the Gauge 1, 1 will be equal to 1. Yeah, so this is just a normalization. And these zeros here, they just denote that alpha 0, beta 0 are the true parameter values. Yeah? And the infinity means that we go back until infinity if you write this as an arch infinity. Okay, and this is the long-term component, so there's a constant, and then it's basically a weighted sum of the legs of some explanatory variable xt. Yeah? And the weights in this case are chosen in a way that they depend on two parameters, omega 1, omega 2. And so this means that you get a flexible weighting scheme, but you have to estimate only two parameters, the omega 1 and omega 2. And in the application, we use a beta weighting scheme. And these weights, they sum to 1. And the pi tilde here, this will give you the sign of the effect of the variable on volatility. Yeah? And okay, this is one way to do it. In this example here, long and short-term volatility fluctuate at the same frequency. But what you also can do is say you can have macroeconomic variables that change only quarterly, but you have daily returns, and then the long-term volatility would be constant within a quarter or so and just changes at the lower frequency. Here we will also assume that the x is a non-negative variable, but I mean, if you have variables that can take negative values, you could just model the log of tau t. And yeah, we will use this names here for the models, Gauge minus RV if realized volatility is the explanatory variable, or Gauge minus X if we use some other variable. So this is again the example with the term spread. If you estimate the model with the term spread, allow for a flexible weighting scheme, then you see that actually the weights that you obtain are hump-shaped. Yeah? So the most weight is given to the term spread lagged about 1.5 years. Yeah? And here you see that you really need flexible weighting schemes. If you use realized volatility as an explanatory variable, then the weighting schemes are declining from the beginning. Okay, now for deriving the test, we rewrite the model a little bit. So if you just multiply and divide by the sigma 0 squared, then the short-term component can be written in this way, where you now have the omega here, so the usual Gauge equation. And I mean, what is important is in this equation here, you divide the squared epsilon by the tau. Yeah? And this is just because when you do this, then this is the same as the h times the z squared. So this is really a Gauge process here. And if you do the rewriting, then the long-term component can be written in this way. And basically what we want to test is whether all the coefficients in this pi 0 vector are equal to 0. Yeah? Because then the long-term component is just equal to 1. Okay? Yeah, so these are the null and alternative. And as I said, when we do it in this way, then epsilon t divided by square root t tau is a Gauge 1, 1, both under the null and under the alternative. Yeah, that's important. Okay, now how to derive the test statistic. Okay, we have to distinguish between this ht infinity, which is, say, the arch infinity representation, yeah, and what we call ht. And this is what you get when you, say, have some starting values at time 0. Yeah, and this is what we will use for the so-called unobserved likelihood, and this here is for the observed likelihood. And in the derivation, we will always work with this unobserved likelihood. And okay, here are some definitions. So this here is the average score evaluated under the null, so at pi equals 0, and at the true gauge parameters, which we denote by eta 0. And for the test statistic in the end, we will use this d pi. So this is the derivative of the likelihood with respect to pi, evaluated at eta 0. If you look at the variance of the score, then we denote this by omega, by this omega matrix. And what we also will need are the second derivatives, which are this j eta eta and j pi eta. Okay, now the assumptions that we need. So under the null, we simply estimate the gauge 1-1 model. Yeah, so we just need first the assumptions for a gauge 1-1. So this is this A1 here. And we assume that the innovation set T has finite force moment. And then these two assumptions, and this is just the Franck and Sakoyan result, imply the asymptotic normality of your QMLE estimator with this covariance matrix here. And this is eta hat QMLE for the model under the null. Okay, then for the test statistic, we are interested in this lower part of the score, so the d pi t. And okay, this can be written in this way. So basically here you have the squared devolatilized returns. Under the null, they should have expected value of 1. And you have this r here. And so I should say this h is the h bar evaluated under the null. And this means under the null, the tau is equal to 1. And so it looks like a standard gauge 1-1 equation here, where you don't divide by the tau. And the r has this form. So it has two components. The first part is just a vector xt, which contains all the lagged explanatory variables. And this part here comes from dividing by the tau in the short-term equation. And it's, again, like a weighted sum of lagged values of this axis. And okay, so in a way, the test in the end will be about whether there is a correlation between these devolatilized squared innovations and this r vector and the elements of this r vector here. Okay, what we need for the asymptotic distribution is then the x should have finite force moments, and we also need an assumption about the moments of the observed process. And then this is just the standard way to write the LM statistic, and here everywhere you have the estimated quantities. And the sigma will be the variance of this d pi, of the d pi. Okay, and the test statistic is chi-squared distributed with k degrees of freedom. Okay, I think I skipped the details of the proof. You can obtain also a regression version of the test, which is simply like the SSR0 here is this sum, and then SSR1 comes from sum of squared residuals from a regression of this on R and another quantity S here. Okay, and what is maybe interesting is if you would be in a situation where there is no gauge, so alpha beta is equal to 0, in this case, the average score looks like this, and then it's just like the Godfrey test for multiplicative heteroscedasticity, because you would just regress squared residuals on a constant and this x vector here. And if you choose as explanatory variables squared returns, then it's the Engel test for arch effects. So this is all nested. And here's the relation to the arch nested in gauge test of Lundberg and Terres-Wirta. So the setup is very similar. The difference is that from the beginning, they assume that H follows a gauge. So they don't divide by the long-term component. And in their long-term, what we call the long-term component, they have a specific explanatory variable, x, which is this psi squared. And this is the squared epsilon divided by h. So this is just a specific case. And this explains why they call it arch nested in gauge, because if you divide the epsilon by square root h and then square, then the squared xi's, they follow an arch process. Yeah? So you have an arch process that is nested in the gauge. But there's now an important difference to our situation. Because you do not divide in this h here the squared epsilon by the tau, their model does not follow, or this equation here is not a gauge under the alternative. Yeah? Only under the null it will be a gauge. And because of this, they look at a similar quantity, but they have here an r, which would be just equal to the x in our case. Yeah? The x with a specific explanatory variable. So if I go back, it's like if I would ignore this second part here. Yeah, completely. This is one difference, and the other difference is that they look at a very specific explanatory variable. Okay, now we have some simulations in which we compare the tests. So all the series are for 1,000 observations. Set T's are normally distributed or T-distributed. We use 3 different gauge specifications with what we call low persistence, intermediate persistence, high persistence. So alpha plus beta is here 0.99. Omega is always chosen such that the unconditional variance is 1 in the gauge component. And then, I mean, there's also the question of how to choose K in the test. And okay, there are some empirical papers that use the model, and if you use it with daily explanatory variables, often they find actually a k equal to 1. But if you use some lower frequency variables or you smooth the variables, then you might also use a high k. Yeah? Actually, like you have a year of lagged observations or so. And I mean, what we think is that you shouldn't use the test for, say, choosing the optimal k. Yeah? You should just use the test to check whether the x has some explanatory power. And so typically it will be sufficient just to look at k equals 1. Yeah? And if you don't find something there, then you don't find it with higher lags as well. So this is the simulation for the empirical size. And what you see that, so this is the Lundberg-Terres-Virta test with the LT. And this here is our test and the regression-based version of our test. And so this is the nominal size here, and these are the estimated ones for low, intermediate, and high persistence. And you see if the set is normally distributed, then the actual size here is very close to the nominal one. That's okay. If we have T-distributed innovations, then all tests are slightly undersized. Yeah? But this is also something that was observed in the Lundberg-Terres-Virta paper already, and also in Halunga and Orm. Okay, then under the alternative, we try to have a realistic example, and so we use data on the S&P 500, and as explanatory variable, we use the daily VIX, and also a monthly and quarterly rolling versions of the VIX, where we just average over a month, previous month or previous quarter, which makes just the explanatory variable smoother in a sense. And then we use this beta weighting scheme, and this here is our tau component. Yeah? And this is just a graph of the 3 different explanatory variables. Okay, and here you can see the size adjusted power. So this first block here is using the VIX as explanatory variable. It uses these 2 values here for omega 1 and omega 2, and this just means that the weights are decreasing from the beginning in the weighting scheme. Yeah? And here you see results for alpha 0.09, so this would be high persistence. This is intermediate persistence. And the K star is the true lag length. Yeah? And in the test, we always use a lag length of 1. And what you see is, so this here would be the Lundberg-Terres-Virta test, the original one which tests for arch, nested, and gauge. And this basically never, or does not detect that there is some deviation from the null. Okay, but it has also the wrong model under the alternative. This here is the results for our test. So for example, this is at the 5% level here, it would reject in 75.2% of cases. Yeah? Here the K that we use in the test is equal to the true one. Okay? And you can compare it with now here what we call a modified version of the Lundberg-Terres-Werter test. There we replace their explanatory variable by the true one, which is the VIX, but still the R is chosen in the wrong way. Yeah? The R is just the X, but does not have the second part. And you see that taking into account the second part is important because here the size adjusted power is much lower than in our case. Yeah? And this holds in all the situations. Okay? And then you might think, what happens if I jump from high persistence to low persistence in the gauge, and you see the power increases strongly. Okay? And why is this the case? So here in the last line I put something which we call the variance ratio, and this is the fraction of the total conditional variance that is explained by the long-term component. Yeah? And so if you reduce the variability of the gauge component, this means the long-term component becomes more important. And so it increases here from 12% to 30%. Okay? And this also means the long-term component becomes more easily to detect for the test. And so the power increases. Yeah? And what you see is when we choose the wrong K in the test, so the true K is 5 or 22, the power gets smaller, yeah, but still you detect that there is a problem. These are two extreme cases where we use this monthly and quarterly rolling window versions of the test. Here the power is much smaller, yeah, but still it's better in our case than in the Lundberg and Terres-Werter case. And okay, this table here shows examples where first, you still have decreasing weights from the beginning, but they are decreasing at a slower rate. Okay, this also means that the power is decreasing. And these two cases are situations in which the weights are hump-shaped. Yeah? So the maximum weight is not given to the first leg, but to some higher leg. And you also see that this will reduce the power of the test. But in general, our test performs much better than the Lundberg and Terres-Werter. And we have also tables where we, choose the correct leg lengths, yeah, with higher order, but actually you don't gain a lot from this. Yeah? It seems that choosing the K equals 1 is typically enough. Okay, and that's it. So we have this LM test for the Gauge-Milas model. It's an extension of Lundberg and Terres-Werter, but now we can use it for any type of explanatory variable. We have higher power than the modified version of their test. And yeah, there are some interesting extensions of this on which we are working currently. For example, there's something like the variance risk premium, which predicts returns. And typically, the variance risk premium is calculated just as the difference between VIX and realized volatility from the last months by assuming that realized volatility follows a martingale difference sequence. But what we show is that when you use this type of Gauge-Milas model, use this to predict next month's volatility, you get a new measure for the variance risk premium, which has higher predictive power for future returns than this simple one here. Okay, thanks.